Hi, so welcome back. In this lecture, we will learn about continuous random variables, PDFs, probability density function, and CDFs, which are cumulative distribution functions, same as before. So this really is a continuation from the previous lecture, where we learned about discrete random variables, the PMFs in that case, when the random variable is discrete, the quantity attached or associated with it is called the PMF and not the PDF, which was the probability mass function. And the CDF is the cumulative distribution function. It remains the same. All right, so what we learned last time is just a quick review of things here. So we learned that x would be called a random variable if it's a function from the sample space S to R, and the image of this x is a function. This, of course, is a function. The image set of this function is called the spectrum. Well, and the elements in the spectrum of x are normally referred to as the spectral points. So this was the example that we did last time. We had a big box, which is the rectangular depiction here. We had 9 balls in there. 3 of them were red, 4 white, and 2 black. So instead of calling them by their names and their characteristic, we called them by numbers. So we numbered all the 3 red balls as 1, the 4 white balls as 2, and the 3 black balls. The 2 black balls as 3. So this was in a way coding the elements which are non-mathematical objects. These are balls. Okay. So this is this big box here is the universal set, which is the sample space S. Of course, 1, 2, 3 are the assignments by x, which is the function, which is assigning numbers to each of these balls. And these 1, 2, 3, of course, these assignments are from the real number set. Okay, so that's the image set or the range set. Now this, not the image set, the range set. Okay, now the image of this x is obviously 1, 2, and 3. These are the 3 numbers which are associated with all the elements in the domain. And so if you collect them as a set, that would be called the spectrum of x. And in this case, because it's a countable set, 1, 2, 3, that's you can count that. This x that we dealt with the last time was a discrete random variable. That's what it is. X is discrete if the spectrum of x, or the image set of x, is a countable set. Okay. So just to remind you again, countable doesn't always mean finite. If it's finite, it will be countable because you can count up to a finite number. But even infinite sets can be countable. For example, natural numbers, integers, rational numbers, these are all countable numbers. Okay, countable sets. Right. So today, so that's the discrete random variable we learned. We also learned about the PMF. The PMF that we learned was really a function that was defined from the spectrum of x to R, but it was really between 0 and 1. And it was defined by f of any spectral point xi. So spectrum will be countable because we're dealing with PMF, in other words, discrete random variable. So you can list them. You can list the elements x1, x2, x3 like that. For example, x1 can be 1, x2 can be 2, x3 can be 3. So if you take any point from the spectrum, the function acting on it is given by the number, the probability that x will be equal to x1, xi. Okay. So in this example, if you wanted f of x1, which is 1, that would be probability x equals 1, and x equals 1 is the event that all the red balls are picked. So that is 3 out of 9. Okay. All right. So that's just a recap. And we also defined what this function was. This is a function from all real numbers to, again, 0, 1. because these are all defined in terms of probability. PMF is defined in terms of probability. So is capital F, which is the CDF, the cumulative distribution function. If for any small x, any real number small x, so please make sure that you understand these x's, this is the capital X, the uppercase x, which is the random variable. And when I write small x, I mean from this domain. This is defined as the probability that the variable is less than equal to this small x. Okay? So in other words, and this was defined, this we had proven the last time, the capital F, which is the CDF, can be expressed in terms of PMF by this summation f xi's, okay, where the so I'll try and write small x as this, okay. I think that would be better. So when I write small x, I'll try and write it as this, running hand x. So, and this is the capital X. So the CDF of a number x, small x, which is a real number, is given by, in terms of the PMF, by all the PMFs of the xi's, where xi's are less than equal to x, and of course these are from the spectrum. Okay, so this was the formula that we had learned the last time, and it's just a review of the things that will be carried forward into this another concept, which is the continuous random variable. So let me, without any further ado, let me just give you the definition of what is a random variable. A continuous random variable, sorry. So a continuous random, so I'll just get rid of all the reviewing stuff and also the heading. We know by now what we're doing. So the definition, so let me write down the definition of a continuous RV for random variable, okay. So here it is. So a random variable x is continuous if and only if the CDF, which is the cumulative distribution function, CDF, which is written as capital F, associated with this random variable x is a continuous function, is a continuous function. Okay. So if you remember, when we learnt about the discrete random variable, the CDF, the graph of the CDF associated with it came out to be, well, in the example that we had learned about those 9 balls in a box, so 1, 2, and 3. So the graph of f in the case of a discrete random variable in that example was a straight line up to 1, not touching 1, and then a jump going up to 2 but not touching 2, and then a jump. So this one is starting from 2. This point is starting from 1. This is going up to 3, and then this point is 1 here. Okay. So if I remember correctly, this was 3 by 9. This was 7 by 9, and this was 1. Okay. So this goes on at 1 for the rest of this axis. So this was the function. This was the CDF. This was the CDF, graph of the CDF when x was a discrete random variable. Okay. Which you can see that it is a discontinuous graph, and we've written that out last time when we wrote down the properties of a CDF. It was left discontinuous. It was continuous from the right, but it was left discontinuous. So it's a discontinuous function. But if we deal with a random variable whose CDF comes out to be a continuous function, that random variable will be called a continuous random variable. And we will do an example of this today. So let's just read that out once more just for clarity. X will be called a continuous random variable. So this is the random variable x will be called continuous if and only if the CDF, f, capital F, associated with this x is a continuous function. Okay. Last time it was discontinuous, so x was called discrete. Okay. So we'll do the example today of a continuous random variable and the corresponding CDF. All right. So let's just do that. So I'll ask a question to demonstrate this, whatever we are doing today. So if I ask you this question, that is, what is the probability? What would be the probability of picking the number 5.9? There's a decimal point here. 5.9 from this interval 5 to 7. Okay, what's the probability? This is a closed interval, box brackets, which means that it includes 5 and 7 and all real numbers in between 5 and 7. So 5.1, 5.2, 5.1381, 6.7892, all real numbers between 5 and 7, including 5 and 7, are in there in this closed interval. Okay, it's called a closed interval. So the question is, what's the probability of picking the number 5.9 from this interval? There are millions and millions, and actually infinite number of choices, because there are infinite number of numbers in between 5 and 7, including 5 and 7. Okay. So if I ask the question in a discrete setting, so for example, let's just draw a separate column here. So if I ask the question, what's the probability of picking just two from, this sample space, 1, 2, 3, 4, 5, 6. It's like rolling a die. If you roll a die, you have 6 possible outcomes. So this is the sample space. And if I ask you what's the probability that you will get a 2, so it's the same as asking what's the probability of picking 2 from 6 equally likely outcomes. The answer was, in this case, so if the event corresponding to this was, the event would be the subset of the sample space. So this is the event I'm looking for, whose probability I'm asking for, because I'm asking for the probability of 2. So in this case, we know what it is. The probability of this set would be, well, number of elements in A divided by the number of options available, likely options, which are number of elements in, so all options are the outcomes, so the set S, and that is 1, number of elements in A is 1, and this is 6. So we could, if you had a discrete set like this, okay, in that case, we could easily answer the question, what is the probability of getting a 2? Okay, you would just divide by the number of possible options, and on top you will have the event favoring the question, which is 2. Okay. Now, what if I ask you to answer this question by the same logic? Can we answer the question by the same logic? So in this case, again, if I take the event A as 5.9, whose, that's what I'm asking. I'm asking if you can pick this number and with what probability. And what is my S? The sample space. The space is all of this, okay? These are all the possible numbers. So experiment, of course, is to pick a number from 5 and 7, between 5 and 7. And these are all outputs. All numbers here can be outputs. You can pick 5.9, you can pick 6.1, you can pick 6.38. These are all, so this really is the whole set is the sample space. And so in this case, while in this case, the probability, the number of elements in A is 1, the number of elements in S is actually infinity, because there are infinite number of elements in there. So by the same logic, if I want to answer this question, the probability would be Well, 1 over infinity, which is 1 from this set A and infinity. So the question is this even valid? Can I even write like this? Is the answer 0 if this is infinity? Or can I even argue like this? Okay, so there are lots of problems when you go to answer this question, which is not really in the discrete setting, but sort of in the continuous setting, because this is not a discrete set. Okay. All right, so let's answer this question logically, therefore, without this kind of an analogy. So, well, actually, we won't be answering this question because it can't be answered by this logic. So, the problem is, hopefully, is that we have the wrong question. Perhaps we need to ask a better question. We need to ask a more relevant question when the sample space is 5 and 7, this closed interval 5, 7. Okay. Actually, if you have to be very rigorous about this, this is both the sample space, and if I want to define a random variable from the sample space to R, I could define any x from this sample space to remain as x in the real numbers, because you see, so what does x do? What does x as a function do? It codes every element in the sample space with a number. For example, in the previous case, it was coding a red ball with 1, it was coding a white ball with 2, like that. Okay, so these are non-mathematical objects which needed some assignment, some numerical assignments. But these are already mathematical objects. X from here will be a number. It will be 6.31, for example. Then I can keep the assignment or the number coding as 6.31, because these are not non-mathematical objects that I have to choose a number for it. So this is a random variable that I can choose to work with when I'm answering a question like this. So in this case, what's the spectrum? What would be the spectrum of x? The spectrum of x would be the same as S, because I'm keeping all, so 5 goes to 5, 7 goes to 7, 6.1 goes to 6.1. So really the image set here is the same as the sample space, which is the domain. And so this is again, and you can see this is not a discrete set. This is not a discrete set. You can't separate one number from another, whereas in this case, the spectrum was really 1, 2, 3. So is in this case. Okay, the spectrum of this example is again 1, 2, 3, 4, 5, 6. That's it. So I can answer questions of this kind by this logic, this naive definition of probability. But in a example like this, where the spectrum is really not a discrete set, I can't answer the same kind of question by the logic that I used before. Okay, so perhaps we need to modify the question. Okay, the new question that I can ask to make, so this is question 1, and I'm going to call this question 2. So the new question that I can ask to make or a more relevant question in a setting like this is to say, so suppose the question is, if you pick a number from this closed interval 5, 7, then what is the probability? What is the probability that the number lies in this interval 5x? Okay, where of course x is a number which is greater than or equal to 5. Okay, that's the question. So I'm saying that if you pick a number from 5 to 7, instead of saying that what is that number exactly, instead of saying that can you pick 5.9, I'm asking, if you pick a number, what is the probability that it will lie in a smaller interval 5 to x? Okay, where, well, x can be anything greater than 5. Okay, so for example, if this is 5 and this is 7 and this is x somewhere here, you're asked to pick a number between 5.7. You can pick it from here. But my question is, what is the probability that you will pick it from this interval? Okay, that's the question. Okay, so let's try and work this out. Of course, x can be more also. Then what's the probability that you will pick it from 5 to x? It gets a little murky here because the question then doesn't, because, well, actually, you can answer this because you have to pick the number between 5 and 7. You can't go beyond 7. The question itself limits you to the interval from which you can pick the number. So even if x is more than 7, what is the probability that you will pick a number between 5 and x? If you pick a number between 5 and x, it will be between 5 and 7 because that's what you're asked to do. Okay? In that case, if x is more than 7, the probability will be 1. If x is less than 7, what's the probability that you will have to pick? You will pick between 5 and x. The probability may not be 1 because this is another possible interval from which you can pick the number from, and you will still remain between 5 and 7. So probability that you will pick it from 5x, 5 comma x, this interval is not 1, but probability that you will pick it from this interval is 1. Okay. Anyway, we will work this out when we are doing this in more detail, and you will see why. Even if you don't understand this logic which I just said. So let's understand this one. Okay. So what I'm going to do now is, well, let's just rub these things out a little bit, create some space for ourselves. So I'm keeping the question here on this side. Okay, I don't need this one anymore. Let's keep this because this was the setup. Okay, now, so how do I answer this question? So the good thing now is that instead of comparing a point to this length, which was the problem, here the problem was, there was no problem because we were counting a number against numbers. So number of elements in A against number of elements in the sample space. But in the previous problem, we were counting number of elements in A, which was 5.9. That was, the number of elements in A was 1. And the number of elements in S was infinity. So this didn't match, the two didn't match. But at least now, the event that I'm looking for is this interval. Okay, the probability that the number will lie between 5 and x. So now I'm comparing length of this interval against length of this interval. Which is better? Because I know the length is a finite number and this length is a finite number. So I can match those two rather than one with infinity. Okay, so here, if you think in terms of units, probably, so number against number matched, so you had a finite thing. This works because length against length. Okay, so that's the clue that we will take, and what we will do is we will say, and this is how we sort of resolve the problem. We say that the probability. So let's write down. So in this, to answer this question, let's say A is the event that the number lies in 5 and x. Suppose A is the event. Then in this, to answer this question, comparing length against length, just as things worked in this case, we would say this would be the length of the interval A, okay, which is the length of this interval against the length of this interval. And really we are taking x, greater than 5 and 7 for the moment. Okay, we're not going beyond 7, which is a case we will explore later. But at the moment, let's just stick to, so here, this length is obviously x minus 5, x is greater than 5. And this length is 7 minus 5, so that really is 2. So x minus 5 by 2. So this can be a possible answer for the probability. Okay. Right. So now, I hope this works. Okay, this is just an experiment that we're doing. Now, let's come back to, we can't say anything more at this point. This is a possible, by analogy with the discrete case, we have sort of resolved the problem, answered a question, asked a different question and answered it in this fashion. So now I draw your attention back to this quantity CDF, okay, which was already defined the last time. It was defined as a capital F, a function defined from the real numbers to 0 and 1. And it was defined as if you take any small x from the real number set, the capital F of that will be defined as the probability that capital X is less than equal to small x. This was defined. And we keep the definition as it is. We do not change the definition of CDF in the case of continuous random variable. This is the definition of CDF once and for all. Okay. All right. Now, if I want to fight for this question, I say this is the probability of this event. If I want to answer, and of course we had already drawn, we said what was the random variable. The random variable was really the identity function x going to x. We already said that. So the spectrum of x is 5, this closed interval, and we've written that before also. So let's just remember that. Now I want to I want to find out what is capital F for this random variable. Okay, this is the question that we're asking. What is the random variable? What is the CDF? What is the CDF F? What is the cumulative distribution for this random variable? Which is, this random variable we are using to answer this question. Okay, let's write that out. So I have to divide, I have to find out from, or I have to categorize small x. I have to know from where I'm picking this x. The question is this x in this interval 5 to 7? Is it not in the interval 5 to 7? So I have to understand that to really find out what is this capital F. So first of all, I will take, let x be less than 5. What happens when x is small x, this x that you're picking, what happens if this x is less than 5? What happens to fx? What is the value of fx at an x like this? Okay. Of course, by definition, it is this. It is less than equal to small x. But small x is now less than 5. The question is, can I have a value of capital X which is less than 5? No, the spectrum of x is equal to 5, 7. So all values of x, the image of x, so all values of x are in this interval 5 to 7. So if you're asking for a value of x which is less than 5, that's not possible. So really this event is a null event. We did a logic like this the last time when we were doing the discrete case, and this is 0. So if you pick this x which is beyond 5 on the left hand side, then the value of f is just simply going to be 0. Okay, let's do another case. What happens if x is greater than equal to 5? But it's less than 7. What happens then? Okay, well, in that case, fx is again, by the same definition, must be less than equal to small x. Okay, and now it's this case, x, capital X. Well, of course, capital X, the value of capital X will have to be more than equal to 5, because all values of x lie in the spectrum 5 to 7. So when I say x less than equal to 5, I really mean x less than equal to x, but it's, of course, has to be more than 5, because all values of capital X, the image of x spectrum, will be between 5 and 7. So what's this? This is this interval, 5 to x. What's the possibility that you pick a number between 5 and x? Because x is about picking numbers. And this really is this event A. I hope that's clear. Okay? And that we've worked out. The probability of the event is x minus 5 by 2. Okay, so we've worked another case out. Now we'll do the last case where, what if x is more than 7, more than equal to 7? What happens then? In that case, fx will have to be equal to, by its definitions, probability that the random variable is less than equal to small x. But if small x is more than equal to 7, it means that, for example, small x can be 7.1. If it is 7.1, what are the possible values of small x that are less than equal to 7.1? Well, all values between 5 and 7. Because all values between 5 and 7 are less than 7.1. What if it is 7? Even then, the possible values of capital X less than equal to 7 will be all values between 5 and 7. Okay, so really, this is the case, this is the event where the whole set, this is the whole set, 5, 7, which is the sample set, sample space. And we know what that is 1. The probability, this is a certain event. So we've worked 3 cases out. The probability, the CDF. And so let's just draw, I want to draw the graph of this function, CDF, capital F, in this case. So let's just draw that. So here it is. This is your x-axis, where I will plot my small x, which is this domain. And here I will plot capital Fx along the y-axis. Okay, so here is 5 and here is 7. Okay, so when you have an x which is less than 5, so all points below 5 on the left hand side, the value of the function is 0. So if I can use another color, so all numbers, all x's below 5, the capital F gets a value 0. So it's 0 up until 5. So I've put that circle in there just to show that it's not touching 5. From 5 to 7, it's a straight line. Okay, this is a straight line with slope half and an intercept of minus 5 by 2. So that's a straight line passing through this point. Okay, and this straight line is going to be it's going to be like this. Okay, with a slope half. Okay, it will pass through this point, which is 5, 0. This point is 5, 0. Because if you put 5 here instead of x, you get 5 by 2 minus 5 by 2. So that is your f, which is on the y-axis, that is 0. 5 by 2 minus 5 by 2 is 0. So it's passing through this point. So it's a straight line with slope half, and it's passing through this. Okay, passing through 5, 0. And if you extend it, it will have an intercept of minus 5 by 2. But that's not important. I'm not going to write it here. I've just shown it because capital F will have this graph below 5. Okay. But even though I've circled this just to show that it doesn't touch, really the graph continues. Okay. Because it reaches here and then this portion actually comes and joins here. So there will be no circle. Okay. There is no discontinuity there. Okay, what happens? So this goes on up to 7, not touching 7. So let's just circle that. So up to 7. And from 7 onwards, what's the value? It's 1. Okay. Now the question is, what is this point? What is this point? Where this circle, where, this line just hits its top. Where is that point? So the x-axis of this point is 7. If you put 7 in there, you get 7 by 2 minus 5 by 2, which is 2 by 2, and that is 1. So you have 1 on the y-axis. Okay. So really, as the line goes and sort of goes towards 7, not touching 7, this y-axis reaches up to 1. Okay. This y-coordinate. Okay. And from 7 onwards, as x is beyond 7 on the right, 7 or beyond 7, the value of the function is at 1. So it's really, from 7 onwards, the value is going to be 1, value of f. And so really, again, there is no discontinuity here. So again, because this line goes up to 1, and this beyond x, beyond 7, this line comes and reaches it sort of lies along 1 here. So again, this is going to be the graph of capital F, which is the CDF. And you can see that this is a continuous function. Okay, there is no break. Like before, there was a jump at every spectral point. But right now, in this function, CDF, there is no jump. It's a continuous line. And that's why this random variable that we're dealing with, whose spectrum is not a discrete set, and because its CDF turns out to be a continuous function, we will call this random variable x a continuous random variable. Okay, so therefore, it's a big thing here. So therefore, x is continuous, and we've just shown that. By showing that its CDF is a continuous function. And that's the definition of a continuous function, continuous random variable. When its CDF is a continuous function, then we will call the random variable continuous. So this is a continuous random variable. Okay, so we'll just finish this lecture with just writing out the properties of capital F in this case. When we're dealing with continuous random variables. Okay, all right. But before, all right. So, and we listed out the properties of CDF when we were doing discrete random variables. So we'll do the same thing here. One important thing that that's worth mentioning is in the case when x was discrete, the relation between the CDF at any point x and the probability mass functions was given by this summation of the function PMF on spectral points, which were less than x. This was the relation. Let's box that. Very important relation, okay, that we did last time. The question is, what happens when x is continuous? Can we express capital F, the CDF, as something like this, a summation. Well, the summation worked out for the case when x was discrete because the spectral points were discrete. x1, x2, x3. So if you calculated the small f or the PMF at these spectral points and you added them. But now in this case, the spectral points may not be discrete. So you may not have a summation, but you could have something like an integration. Okay. So we will, let's just see what happens here. Okay. I claim, okay, that you can find a function which if you integrate, so this x is the highest, the summation takes all xi's up to x. Okay, so x will be the highest or the upper bound for the spectral points. So similarly, by that logic, I want to find a function whose integration up to this upper bound small x, and the lower bound, the lower limit will be minus infinity because we are taking all spectral points below x. So there is no restriction of where the spectral points can go to. And by that logic, I can take the lower limit to negative infinity. So I'm looking for a function. Okay, right now I'm looking for a function ft. I'm going to call it ft. I'm not changing the name from discrete to continuous, but I'm looking for this function. I'm looking for this function such that if I integrate this function, by analogy, I'm looking for this function such that if I integrate this function from minus infinity to this, maximum point or this upper limit x, I will get the CDF, okay, in the continuous case. Well, let's come back to the example that we were doing. Well, when x was, you remember that when x was between 5 and 7, in the example that we did where we were picking numbers between 5 and 7, the fx, the value of fx was x minus 5 by 2. We just worked that out, just before I just rubbed it out. So I'm looking for a function f t such that if I integrate up to x from minus infinity, I should get x minus 5 by 2. Well, it turns out it's very easy. If I, instead of this function, if I just put half, okay, I would get it. Why? Because this function, this integration, I can break up between minus infinity to 5. Oh, sorry. I'm going to keep ft for the moment. Okay. I'm going to, so this is, I can break up this integration in two parts where I'm integrating from minus infinity to 5 and then from 5 to x because x is more than equal to 5. Okay. Now, if I substitute half for f, if I substitute half, and for f, if I substitute 0, then I get x minus 5 by 2. Why? Because if I substitute 0 for f here, in other words, f is 0. So there is no contribution. So integration is 0. So I get a 0 from here. Plus, if I get half instead of, it's a constant function, I'm looking for, remember, I'm looking for this function. I'm claiming that if it is half, it's a constant, I can take out the half and you will get x minus 5 because integration dt from 5 to x is x minus 5. So x minus 5 by 2. And that's this. So it's telling me something. It's telling me that this function, which I'm looking for, if x is less than 5, okay, so I put in 0 here, when I was integrating f from minus infinity to 5. So in other words, when this t was less than 5, let's write in terms of t, because I've written f in terms of t. Doesn't matter, I can write x, it's a variable, okay? But since I don't want to confuse the variables here, so when t is less than 5, of course, in the range from minus infinity to 5, t is less than 5. In that case, f was 0. That worked to give me this function. And when t was between 5 and x, dt, this is between 5 and x, in that case, the function was half. Or what? Okay. And what would happen if t was more than 7? If x is more than 7. Oh, what am I doing? Yeah. Well, actually, sorry. When this you can take. So the question is, how long can you take? So how much can you increase x? X will be less than 7. So how much can you push x? Can you take it to 7? Okay. If x becomes close to 7, okay, then this becomes 7 minus 5 by 2, which is 1. If x becomes close to 7, then this becomes 7 minus 5 by 2, which is 1. So yes, you can take x really up to 7. No problem. Do you see that? X was a variable. It's a number between 5 and 7. So the question is, how much can I push x? I can take it up to 7. And still the two sides would match. So that's why instead of writing x here, I've taken x to the limit, which is 7. Okay? And similarly, what happens if, finally, if this t is more than equal to 7? Well, I claim that this will be 0. I claim that. Why? The 0 should work because we worked out capital F. We worked out capital F just in the previous board, and it was just this, exactly this. Okay, if you remember. All right, let's just finish this without going there. We can do it from here itself. So what if t is more than 7? In that case, if you remember the graph of f, capital F, after 7 it was 1. Okay, so if you take a number x which is more than 7, okay, then if you take a number x which is more than 7, then the capital F of that number is 1. Okay, because that was what the graph was telling us. Okay, so I'll just bring you back to what we are doing. This is what we are doing. We are done with this case because we have established it. I'm looking for this function, and the only piece left is we've worked out when x is, I've written this in terms of t, but you can write it in terms of x as well. So what happens when x is more than 7? That's the case I'm looking for. What would be the value of this function? When x is more than 7, we already had shown by the graph that capital F will be 1. So I have to look for a function. Okay, what would be the value of this f beyond 7? Okay, so again, by the same logic, I can break up this function up to 5. I can take it from 5 to 7. And then I can take it from 7 to infinity, or 7 to x, because x is more than 7, more than equal to. The question is, what is f in this range when t is more than 7? See, t here has to be more than 7 and up to x. Okay, so now, of course, in this range, when t is below 5, we have already established that this is 0. When t is up to 7, we have established that this is half. See, from 5 to 7, when t is going from 5 to 7, this is half. So if you just do half, that you will get 1. Because half, that's a constant that comes out, and integration dt from 5 to 7 is 2, so 2 into half is 1. So we have already matched the two sides. There's one on the left hand side, there's one on the right hand side. So this tells me that this, on this interval, or this integration will have to be 0. And it can be 0. One of the ways it can be 0 is to make the function 0 beyond 7. So if t is a number which is beyond 7, let's just make that 0. And we have a function. So we actually found out the function that we were looking for. It's this function. And it tells us that it matches with this. Okay? It just matches. Okay? If you integrate this function now, you will get fx because that's how we found it. So in other words, we have found the analogous function f in the case when x is continuous. Okay, so we're not looking for it anymore, we just have it. We've established it. And this function, this new function, is called the probability density function, or the PDF. Okay, this is called the PDF. This was called the PMF. This function in the case of discrete random variable was called PMF. And this is PDF. That's the difference. They're very much the same. One is the summation because the spectral points are discrete, and the other is an integration because the spectral points are not discrete. And in this case, this associated function, which on integration gives us the CDF, is called the PDF, probability density function. Okay, I think just last couple of things. We will finish this very quickly with listing out the properties of the CDF in the case that it is continuous. Okay, so properties of CDF in the case that x is continuous. Okay, let's just finish that. Let's remember what was the graph of the function. So as an example, from 5 to 7, the graph of the function was 0 up to 5, then it went on in a straight line up to 1, and then it remained 1 beyond 7 as well. Okay, so this was capital F, which was the CDF. This is the graph. Well, you can see that as before, as you go towards minus infinity, the value of f at negative infinity will have to be 0. And this was the same thing that happened in the case when x was discrete. Okay. Similarly, if you take x to infinity, that if you go beyond the last point, spectral point, it remains 1, sort of achieves 1 by the time it reaches infinity. So this goes to 1, and we have seen that in the previous case as well. There is a difference between the CDF in the continuous case and the CDF in the discrete case, in that the CDF in the continuous case is a continuous function. So f here is a continuous function, which was not the case when x was discrete. It was a step function which was left discontinuous. Okay, so that's a difference. And the fourth one, in the case of discrete random variable, we had sort of a formula for the probability mass function at a spectral point A, This was given by f of a plus minus f of a minus, which is the right-hand limit of capital F at a and the minus the left-hand limit. The question is, can we have something similar? This was in the discrete case. The question is, can we have something similar as a formula for PDF? Okay, we'll just work that out very quick. Of course, this is the formula for PDF. This is how CDF is connected to PDF. If I take A as a spectral point, as it is here, A is a spectral point. If A is a spectral point, then suppose I look at the CDF at a point which is nearby A, so A plus delta A, and I subtract off from there the value of the function at A. Well, from a little bit of analysis, we know that this is almost equal to, up to order 1, this is equal to the derivative of the function capital F at the point A multiplied by delta A. It's almost equal to, up to order 1 from Taylor's theorem. And if you use this definition, A plus delta A minus capital F of A will be, well, this integration tells us it's an integration, this formula tells us it's an integration from minus infinity. The first one will be A plus delta A of ft dt minus, this is integration from minus infinity to A, because there is A instead of x there, ft dt, and that really would be the integration from A to A plus delta A, because this integration includes the integration from minus infinity to A and goes beyond up to delta A plus delta A. So that gets subtracted with this, and so you're left with ft dt. And of course, this is the Riemann integration over a very small interval. So it's almost equal to small f, the value of f at the point A, multiplied by this interval fa delta A. So if you compare these two, see, they're equal. The left-hand sides are equal, except the right-hand sides are, the expressions on the right-hand sides are not. But because the left-hand sides are equal, these two must be equal. So this one and this one must be equal. If they are equal, you can cancel off delta A from both sides, because that's a non-zero number. So what you're left with is FA will be ddx of f at A. So it's not this anymore. It's not this anymore. It does have an expression. It's the derivative of capital F at the point A. That's the formula of how small f can be expressed in terms of capital A. This is the formula how capital F can be expressed in terms of the PDF. Okay. All right. So those are the properties when x is continuous. So I think we will finish with that here and take things off in the next lectures. Thank you.